Hi Janice, nice seeing you connected. Hi Jayanta, nice seeing you connected. Oh, Mahima, uh, thanks for connecting. Nice seeing you here. Hi Kristen, nice seeing you connected. Hello you, how things are going for you? I think on Monday we were disconnected. It was for me as well, and I wasn't able to reconnect back. Okay, I think we have a lot of attendees, and it should work for everyone. We may also get Elisha connected. It is the summer high school student who is just making a shadow of computational program for a couple of weeks. She will maybe connect for the second half. So there, thank you for connecting and for dedication to this class activity. This is a computational chemistry course which has a goal of going over basic background for theories which we just need to tolerate. We do not have much of exams based on theory background. We just need to pick up the terminology and get basic concepts. And most part of the course is accumulating skills for building molecular models and computing properties of molecules and structures by appropriate methods. And then there is a little component of comparing to experiment and discussing through scientific communications. We did complete first chapter on molecular models and geometry optimization, and now we are going over the uh, first and simplest electronic structure method, so-called Hartree-Fock theory. The theories that we are going over um, has minimal practical use, but it is an important cornerstone for any computational chemistry activity because it is one of the theories that is proved on the very exact mathematic level, and terminology from and concepts from this theory are used throughout any other theories. I do see that it looks like if we count today's meeting, there is one, two, three, four, 5 meetings approximately to cover the theory and do relevant practical skills. And on the sixth meeting from now, I suggest we do another session of when class attendees will share next layer of practical skills. So please join me and follow the suggestion to make a little sign up activity. So we are going to present skills that we are doing right now in the lab part in about 3 weeks from now, and I'm going to share the link that would allow to sign up for this activity. So here are the skills that seem relevant to goals of the class, and I'm going to bring up the Google Slides document where one can look on it and type in your name. So if you have more than one subjects or groups of subjects that you want to cover, feel free to write down your name. I will try to optimize choices. So while we need to feel it right now, but do not rush. I'm going to speak for a minute what are the subjects and how you can group them, which are absolutely necessary and which can be skipped. While I'm speaking, it is not 5-7, it will be like 9-12 because we do larger number of labs. Before it was only one lab per week. So please, I invite everyone to follow this link and log into this Google Slides. Right now I do see only 2 class attendees are looking, and since it keeps it wants to keep all of us anonymous, it shows these 2 symbols, pink and cyan. So please follow the link that I did send in the email and the chat room. So the first part that the first part is basically selecting the options in Gauss view for setting up electronic structure method. And if you do not want to do all of them, you can select maybe 1 or 2. So right now we are selecting Hartree-Fock as electronic structure method. Then we briefly mentioned basis set, and nomenclature of basis sets is something that is useful, especially if throughout your scientific career you plan to work with small molecules. List of available tasks. By now we did only energy and optimization, but there are some additional tasks that one can compute. And again, if your life destiny is chemical reactions, there is one opportunity called transition state search. So if you are wet chemist, organic or inorganic chemist, you may it is recommended to consider seriously this list of available tasks and specifically focus on transition state search. So we will add this quickly here. Transition state search. So it is very recommended to Mahima and to Jayanta. I am aware of your background in organic and inorganic wet chemistry, synthetic chemistry. So please consider this option as something relevant to you. Now, last time we were preparing a way to initialize electronic structure calculation through mouse operation, through Gauss-View software. This is not high throughput task. If you plan to do like 1,000 calculations or 100 calculations, if one needs to do it professionally, then clicking on mouse 1,000 times is too much. So things are typically done in operating text, input text files, and modifying it. So preparing input file, specifying memory, mentioning what is spin and multiplicity. I think in the whole list, this one is the simplest. This is the simplest task. So the next one, how to analyze output of Gaussian calculation without Gauss-View. It is a subject of our today's practical lab. It is what we are going to do today. So please consider to so it is a heads up, and after today's meeting and maybe next lab meeting, this will become crystal clear. So this is also one of the basic vital skills. Symmetry groups in Gaussian software, it is very optional. We typically do it if there are excessively large number of attendees for the class. So unless you specifically interested in this, this can be skipped. The extracting density of states of .log files and draw numerical data with GNU plot software is unavoidable. This is one of the key parts of the course, and is, I don't know, is it easy enough or complicated enough, but this is important part. Density of states is something that we will be covering later, but this is a way to visualize electronic structure in a graphical form applicable for humans. And molecular orbitals and all details how to generate them is what I would select for myself if I would be taking this class as a student. So it's easy and fun part. The orbitals for open shell configurations, if you are dealing with singlets and triplets, non-singlet configurations on one hand, or if your research involves transition metals, then open shell configurations could be your choice. And Mulliken charge is quite an easy task that can be added to one of the major sections for inspecting if the system experiencing redistribution of charges between its atoms. So I invite everyone to keep looking through this list and type your name near one of the or several of the subjects. If you need more input data or ideas, I will be very happy, and I will look on it at the end of our meeting, hoping to see more selections. So some choices to select. Basically, let me so that we time management. Oh, hi, Alicia. Thank you for joining. We are going over plans for presentations that will be in about 3 months, and then there will be theoretical background that you may just wait until it is done as an entertaining part, and then in maybe hopefully within 20 minutes we'll go to the practical thing. Oh, Kristen, thank you for the choice. I just type the name of all class attendees. Maybe it will be easier to connect names and subject by arrows. Mahima, so we need to select 3. Well, the things that are enclosed into the boxes, it's kind of one task. It's a lot of words, but they are easy. But if you want less than 3, feel free. We need to cover most of these subjects with all available class attendees. I'm just typing the names. And maybe FAM will join later, maybe not. So I see someone is considering symmetry groups. Okay, so please keep working on this table, and I will try to look how the filling of this table goes. Oh, thank you, Mahima. Okay, I'm impressed because symmetry groups are not easy. You're brave. So we need to go through the slides, but the connection remains active. So for the homework, there will be 2 parts, one theoretical, and this simple equations will take like 5 minutes. If you cannot do it in 5 minutes, just skip it. And computational part will be report so-called homo-lumo gap for a range of models. And it is what we will be doing during our practical part. So last time we were running Hard2Fork for titanium hydroxide, which is the simplest model for metal-organic complex. And after the .log file is generated, we were looking on the total energy. After the total, so we need to slowly learn how to operate these calculations without the graphical software. Do everything in a command line. So input file. So instead of clicking Hard2Fork and basis set, one can just write a couple of lines at the beginning of the file. Then after the job is complete, there is a so-called .log file. And by looking and analyzing this .log file, one can learn basically any property of a molecule, assuming that Hard2Fork and selected method and basis were appropriate. And specifically, we are going to identify list of so-called molecular orbitals and look for the border between occupied and virtual eigenvalues. So these 2 blue and red numbers, and then subtract them and multiply by a constant of 27. And this number, the energy offset between occupied and unoccupied orbitals, corresponds to the color of the molecule or material. So if it is above 3 electron volts, it likely will be white or transparent, which agrees for this complex. If you will take another complex, it will be small, like in the range of 2, it's bright colors. Below 1.5, it will be often black because of absorbing infrared. And then we will be building oligomers when more than one titanium atoms are connected through oxygen, and it is our path to go. So it was an overview, and whew, oh, I see you are interacting in the chat. Sorry, I didn't notice it. Thank you for sharing the link. So, what do we expect to have done by today, in a sense of a theory? We need to get acquainted with so-called Slater Determinant concept. And we have already introduced this concept last time, but it is one of the fundamental concept of the overall modern science, so it's not a waste of time to speak a little bit more about it. So if you don't care about equations, you just wait until I'm finished. Or another option, if you think that equations are shown here are very clear to you, you can also lean back and do nothing, because I'm not going to introduce anything beyond these two equations. So there is a Slater determinant is a way to compose multi-electron wave function out of one electron orbitals, called here F and G. And in order to match Pauli exclusion principle, there is a product of two orbitals repeated twice, 1 and 2. Orbitals are the same, there is a minus between them, and the arguments are swapped. So for orbital F, argument was 1, in the second term it is 2. For orbital G, argument was 2, in the second term it is 1. So this rule to compose multi-electron wave functions out of one electron orbitals is needed to match Pauli principles, to forbid two electrons to sit in the same orbital. And mathematically, this equation comes from just computing determinant of 2 by 2 matrix. If there is larger than 2 number of electrons in atoms, it will become longer chain with bigger matrices, but the concept is the same. Anti-symmetry means minus between these concepts. Whew. Okay, I'll try to be as quick as possible. Oh, skip. So here is our plan of building oligomers of titanium hydroxide. So 1 titanium, 2 titanium, 3 titanium, and I will go over it in practical part, but it is suggested that one should try to build, to open separate directory for each model, otherwise it will become messy quick enough. And last time we were looking only on the total energy, but today we are going to look beyond total energy. We are going to look on the so-called band gap energy, which is responsible for the color of the model. So please practice your patience. I'll try to go over slides as quick as possible to match our main goal of picking up concepts. So here is approximate plan for the Hartree-Fock theory. So it rests on several concepts, and we are going to cover them slowly but surely. So first concept is Slater Determinant. Then there will be concept of so-called mean field, and then there will be concepts of correlation and exchange, and then there will be actual algorithm for Hartree-Fock when everything is combined together. Mean field is the most important. Today we deviate from this flowchart, and we speak a little bit more about how to justify this functional form of antisymmetrization of Slater determinant. And this all is based on the concept of spin. So we are looking, we have separated electronic and nuclear degrees of freedom. And for electronic degrees of freedom, we are solving time-independent Schrödinger equation with total energies, a total energy of all interactions related to electrons are stored in this Hamiltonian operator, kinetic energy of electrons, potential repulsion of electrons, and attraction of electrons to each other. And this big psi function is composed of smaller phi functions by practicing determinant. So this form of taking determinant is connected to the concept of spin. So when we, all of us were taken some level of high school chemistry or maybe freshman chemistry, and there one is often looking onto hydrogen atom wave functions. So there, and I will try to be quick, but I'm sure if I make stops and ask everyone to participate in discussion, you will be able to explain it better than myself. So if we do have a wave function for hydrogen atom, this S, P, D orbitals, right? So this wave function is characterized by 4 quantum numbers. Principal, which tells how big energy of the orbital is. Then orbital quantum number, which shows how quickly electron rotating in general, what is the component of kinetic energy originating from rotation. Then magnetic, which tells which direction, forward or backwards, electron is revolving around nuclei. And spin, which so what I'm going to say, please never repeat in public. So it's only pedagogical trick, which is scientifically not ideal. So spin is assuming that electron is a charged sphere that rotates clockwise and counterclockwise. So depending on the direction of rotation, it has different magnetic moment. In fact, it is just abstract concept, because if one assumes this model of quickly rotating sphere, the circumference point should rotate quicker than speed of light, so it's not good. But spin is a quantum number number 4 for electron and hydrogen atom, and it has only 2 values, discrete values. I'm going to spend most of the time before we go to practical part in bringing more details in how to treat the spin mathematically. Which mathematical operations are needed to treat the spin. So when we do regular elementary math, we divide, subtract, do fractions. When we do calculus, we do differentiation, integration. But for the spin, one needs, and one can use only very specific part of today's math. It is matrix algebra. If you never did it, it may look scary, but I will try my best to convince you that it is easy and practical. because it's a spin is the simplest quantum object that one can describe. So notations, if it rotates clockwise, it's plus, counterclockwise minus, and people use notations like plus, minus, 0 and 1, alpha and beta, up and down. And if one wants to practice flip of the spin, then one needs to introduce operator of spin flipping. So if one applies spin raising operator to spin down, it will flip up. If one applies spin lowering operator, then spin up will convert to spin down. And in the following, you will see this little angular brackets, which is just common notation in this theory. So what are these spin flipping operators? How we can wrap our mind of our regular everyday thinking around this concept. So suppose we have a bird, an owl, and suppose we have a wizard that makes a hocus pocus and converts an owl into a skylark. So if we express this operation on the same mathematical language as one uses for spins, we will write it this way through angular brackets. So we should start looking from right. So originally we had an owl. Then a wizard approaches from left to the right. And as a result of this operation, we are getting skylark. If the angular brackets are oriented in different direction, it is an analog of scalar product, and it means compare these two objects. So if they coincide, it will give 1. And these angular brackets are called bra and cat, because like bra is one part of bracket, cat is another part of bracket. So if the objects coincide, all with all, comparison gives it is the same object, it's 1. If you have skylark and skylark, comparison of these two objects gives also 1. And if we compare objects of different nature, their comparison gives 0. Okay? And if one swaps the order, but still it is different objects, it will be still 0. Now, a little bit of another, if the angular brackets facing not outwards but to each other, then this construction means convert the object from the right into the object which is on the left of such construction. And on if sophisticated language, it's called dyadic product. So converting all into the all means identity, changing nothing. If one has all on the right and skylark on the left, it will be the wizard that converts all into the skylark. So here is our all, right? Here is our operator, our wizard, and right now we do have 3 birds, and we group them first and then 2 in different order. But we can think on it in a different way. So look on the scalar product, bra and cat, all with all, and then they will cancel, give us number 1, and as a rest we will have a wave function of the skylark. So this is how the Dirac notation for quantum theory works. And one can try to apply the same notations for this alpha and beta. So if one has alpha and applies this operator with alpha and beta, we put this blue box and cancel alpha, and then we get beta. Okay, so please ask questions in the chat line or through the voice, and I will speed up to the main thing. So if you are fine with material up to here, you will be able to successfully complete the theoretical part of the homework. The remaining thing is more boring, and I will glance through it very quickly. So if you have two spins, then one needs raising and lowering operator for each of them. There will be S plus and S minus for first and second spin. I will go very quickly because otherwise we will not be able to do the lab. In general, system can be in the superposition of alpha and beta. And in order to find the no, this is not needed by now. I will go very quickly. No, this is not it's all good, but it is not what we need. I can go with those of you who are interested after we are done with overall part. So here is a little dictionary how to interpret this alpha and beta spins in form of vectors, 0 and 1. So it's same as vectors in two-dimensional space. We can have motion along x and by 1 and 0 along y, or we can have motion along y and 0 along x. So in some sense, those are two-dimensional vectors. And if it is in between alpha and beta, it is a vector with some angle. And the spin conversion operators are 2x2 matrices. Okay. Just close your eyes and be patient for 2 slides more. So suppose we have 2 spins. Therefore, for first spin, we do have everything with index 1. For second spin, for second electron, we have everything with spin 2. In order to find eigenstates of the system of 2 spins, one needs to apply operator of total spin to this wave function and find its eigenvalues. If one opens this product of 2 brackets, so 2 terms in each, there will be total 4 brackets. And the interpretation of each term is the following. So first one is probability that we have both first and second spin oriented up. Last term is a probability that both spins are oriented down. And the cross terms is a probability that first spin is oriented up and second spin is oriented down. And here the term probability that first spin is oriented down and second is up. By solving the equation in the top, one can find these probabilities C1, C2, C3 for eigenstates. And if one performs this procedure carefully, then the lowest energy state will be first coefficient is 0, last coefficient is 0, which means it is improbable that both spins will be up, and it is improbable then both spins will be down. And the coefficients in the middle will come to the following configuration: 1 divided by square root of 2 and minus 1 divided by square root of 2, which means it will be equal probability with amplitude of probability with minus sign that they are up and down, and then with down up. So this functional form of up and down minus down and up is exactly the same as was suggested by Slater for any multi-electron function. Whew. So if you tolerated this story about spins, you should believe from now on that the Slater determinant equation is correct and we can use it. If you have some doubts, I will be happy to keep proving it, but maybe on the one-to-one basis so that we do not experience patience of everyone in the class. So this is what we recently got on the previous slide. So up, down, minus, down, up. And by functional form, it is the same as suggested Slater determinant. So 1 over square root of number of particles, and in the brackets, first it's equivalent to up, second orbital equivalent to down, and then the first electron in state down, second electron in state up. So by practicing linear algebra for spins, we can justify the Slater determinant concept. Okay, we are done with theoretical part. Now let's go to the practical aspects. So I'm inviting everyone to open MobaXterm if you are working with Windows PC, or Terminal if you are working with Mac, and please log in to the Photon server. So the goal of our exercise today will be to find the color of the model by computing the HOMO-LUMO gap. So I will try my best to look into the chat room for the typed questions, but if you do not see me responding to questions, please do not hesitate to switch on the microphone and attract my attention. So I'm really willing to interact and help everyone, but you know that sometimes people get excited and stop looking around. So right now I'm on the local computer. Just in case if so. Before I log into the Photon, I want to bring up that for some of classmates, the Gauss view on the Photon doesn't perform as ideally as we may wish, and therefore some of us are preparing models on the Avogadro on local computers. So if you need to prepare titanium dioxide model on the local computer, I want to bring, let's open new file, new. There is a little trick to prevent us from an error. So in order to draw titanium, I'm clicking in the Avogadro, I'm clicking this pencil, then select an element, and I do not see titanium. So I click other, and it brings up the periodic table for me. So in the periodic table, I'm looking for the titanium, and after selecting titanium, I can just click once for titanium atom, and then for element, I can select oxygen and connect 4 oxygens. So if we look into electronic structure of titanium, we will identify that on the valence shell it has 2 s electrons and 2 d electrons. And if we look for stable oxidation states, one of the stable oxidation states for titanium is 4+, which means when we compensate it with 4 hydroxyl groups, OH-, total charge is balanced. So titanium is 4+, and we have 4 hydroxyl, which is 1-. So I did place them together, and then I want to make it better for slightly optimized geometry. If I do UFF, it will make the wrong direction of optimization. So UFF, as soon as we have metals, we cannot trust UFF. We need always to try different things. So it does make molecule square planar, which is not correct, as we can see later through Hartree-Fock and DFT optimization. So, but luckily, among the list of force fields, there is a G chemical, and it will do a little bit wrong interatomic distances, but it will arrange correct spatial arrangements, a so-called tetrahedral orientation of oxygens in respect to titanium. So this is a good starting point. I'm saving it. Save as. Practicing a little patience. Okay. Titanium 1, oxygen 4, H4, G chemical dot PDB. Save. So now I do have this model in my local computer. If Gauss view will fail for me, I will transfer this file to Photon. If I will be able to do things with Gauss view, I will just draw it from scratch, or use a model that was created last time. So I need to connect to Photon cluster. So I'm typing SSH, then -y for graphical connection, username at photon chem ndsu no.edu. So it doesn't answer because I did a typo. Let's do it over. Repeat it. And now it asks for the password. Okay, I was lucky to type the password correctly, and just in case, I know that you all are already a certified experts in Linux connections and operations, but just in case, let me copy this command in the chat line. Now I'm going to the to the directory which is assigned on this server for our exercises. And I'm going to my subdirectory pwd to check where it is, and ls to check directory. So I'm opening the make directory 10 cd 10 pwd. So just in case, let me cd space and then the path to the directory for the class. I did type it into the chat line. So in here, so copy, and I'm going to exit and enter, but you don't need to repeat it. So scp everything, and I have only one file into so I want to copy this PDB file into the server, and it asks the password, and the this PDB file is transferred. And then I'm logging once again. Okay. And just in case, if the file transferring can be done in the mobile extern, at the left panel there are a way to just pull, drag and drop files. So this scp command is just replacement, which would work a little bit more reliable. So I'm going back to the directory where we practice everything. cd directory. I have this file, and now I am opening gaussview.exe. I'm putting this ampersand shift 7 symbol at after the name of the command. Without this symbol, it will block command line from typing new commands. But with this symbol, I execute graphical application and still keep ability to type commands. Okay, so some of us have already computed ground state electronic structure of titanium hydroxide in the previous meeting. If you have done it, you may look through the slides of today's meeting and find your own way to extract HOMO-LUMO gap, band gap, HOMO-LUMO gap between occupied and unoccupied orbitals. Just in case last time you didn't complete electronic structure, I will do it over today. We need to be sure that we all are on the same page and everyone has the same data in his or her directory. So if Gauss view is working as it should, I'm selecting titanium, click, selecting tetrahedral, clicking in the white box, and then selecting in the periodic table oxygen and replacing this artificial hydrogens by hydroxyl groups. So by now I do have titanium hydroxide fabricated by Gauss view, and I can, before starting any calculations, I can file, save, someone is creating models in the subdirectory with my name. So it's okay, but it's better to go into the subdirectory labeled by your name. You do not need to erase it here. I'm grateful and I can use files this TI2, TI3, TI4. Thank you. I will open and show it to everyone, but for right now we are on the learning curve. But as soon as we go to more advanced calculations with the main challenge, it sounds ridiculous, but main challenge is bookkeeping of the directories to avoid the mess. So arrange set of subdirectories and label them accordingly by name of the author, by name of the system, by name of the method. So when it gets larger than 20 jobs in your simultaneous processing, lack of organization will make it impossible to navigate. Okay, so I am saving this input file as I can call it again titanium 04H4 and hand draw gaussview.com. So it's just a structure. Now, if my Gauss view doesn't work, if it works only for menus but does not allow to draw, I still can open the file that I have uploaded. So the file was created in the PDB format, and here it is, underscore G chemical. So I did open this file, and you see the interatomic distances are a little bit more ugly than needed, but it's something reasonable. It's tetrahedral. We can measure the angles if we need to, and check if they are if they correspond to tetrahedral orientation. Also, one can do a quick optimization by clicking this clean, but it is not actual optimization when so you see it expands the bonds. one should be very careful. The results of this broomstick are not reliable, and such results are not publishable. It's only input for future calculations. Now, repeating what we did last time. So, even if your white panel in Gauss view doesn't show the model, do not worry, do not panic. If look at the bottom line, if it shows 9 atoms, 58 electrons, neutral signal, it means it has successfully downloaded the file, and you can go with calculation further. So now we are going to calculate Gaussian calculation setup, and I'm practicing a little of patience. So energy is fine. I do not want to do optimization with Hartree-Fock method. So before 2 meetings ago, 3 meetings ago, we were doing mechanics. Now we are doing Hartree-Fock. In a month from now, we will be doing DFT. In a month and a half, we will be doing the excited state TD-DFT, which is TD-SCF. Right now, we do not need it, but just for your information, TD-SCF is what you need to do optical properties with Gaussian. And I think, well, each of us could be interested in optical spectra. Alicia, you, Janice, Kristen, Mahima, Joanta, it's quite standard characterization. But now we are doing ground state, Hartree-Fock, and selecting basis set Reno 2DZ. After this, I click submit. Just save, and I add the name HF, and then tell the basis Reno 2DZ. Save. Submit the following to the Gaussian. Practice patience for a couple of seconds, and then it shows Gaussian jobs completed. There are 2 output files. I select the one that ends with log and click OK. So it's just the same thing, it just rotates a little bit. And now if I click on the results and click summary, there will be a menu that pops up and shows this minus 359 atomic units completed in 1.7 seconds. So this is the place where we stopped last time. Now, so if you are preparing to report a homework, you can copy paste this number 359.36 and put it like single titanium hydroxyl group gives total by Hartree-Fock gives total energy minus 359. Now, can we get the same information without mouse operated thing, just in a command line? Again, motivation for the command line is if we need to do more than a couple calculations. So it is more professional, productive, high throughput. So I'm looking ls minus lt, which means show the file that was created last. So last file was created is titanium hydroxide Hartree-Fock 2dz.log. So, oh, I see someone is doing is already doing the calculations for density of states and extracting virtual and occupied. This is really cool. So I'm happy to see it. So I do want to look inside this file, .log file that is highlighted in blue. So I'm typing more and then repeating the name of the file. So just in case, like you do not need it, but just in case, so that everyone is on the same page, I am pasting this more .log file. And then this file will be maybe 50 pages. The bigger the molecule, the bigger the file. And it shows its lab journal, like of the Gaussian software. It writes down everything it does. So first it gives credit to authors, then it tells, I have read the coordinates, and I'm trying self-consistent cycle, doing several iterations using the basis. And there are technical details which we do not care right now. And what we do need is, so it's about 75% towards the end, oh wait, we will need this table of alpha oak and alpha virg very soon, but if one scrolls through, there will be the line that tells the same information as one can extract with the Gauss View software. So I'm copying this line. So grep means find the line in the file that includes this keyword SCF. So if I'm looking, it is a line 204. So if I'm looking into the whole file, and escape column 204. So in the line 204, there is a SCF done, energy restricted Hartree-Fock. Restricted means we do not care much about spins. We know that in this system number of spin up and spin down is fixed, and minus 359.36. So this is the information that we may want to report for the homework or lab report, however you call it. So please save this information into a Word file nearby the figure of the molecule. So by now we are completely done with our previous meeting. Now I'm going to escape. If I look once again through the file, going through the file and near the 75% of completion, I want to bring your attention, attract your attention to this table. So it has alpha OCC and alpha VIRT. Let me get a little break and ask everyone, how would you interpret this table? So please type in or answer with a microphone. Joyanta, do you have any ideas about this table? Okay, that's fine. Let's check. Mahima? Anything? Oh yes, yes. You many thanks. Occupied, unoccupied orbital. Thank you. You. This is correct, but I want to hear a little bit more feedback. Kristen, can you explain by your own words how you interpret this table? Just briefly. So what are, okay, Kristen, giving the eigenvalues that correspond to those orbitals which are occupied versus unoccupied. Very good, very good. Thank you. And Janice, I think most everything is covered, but do you have any other comment of how to interpret this table?
Electron orbital are the ones you want to look for when determining HOMO-LUMO calculations.
Mm-hmm. What is your observation in this list? Are energies random or they are ordered?
They're ordered.
So are they going from uh, larger to smaller or from smaller to larger?
For the occupied electron orbitals, from top to bottom, it's going for lowest, sorry, highest energy to lowest energy. And for the virtual orbital, it's going from lowest to highest.
Um, I would say they all go from lowest to highest because minus, the dash in front means minus.
Yeah.
So it
Yeah.
goes from very negative, then approaching zero, and then going higher up.
Yeah. And then same goes for, virtual. Mm-hmm.
So this is very much related to the Aufbau principle that one is getting in high school chemistry. Like in hydrogen-like atom, one first feels one s orbital, then two s orbital, then two p orbital for atom, and for molecule the same. One orders all orbitals in the ascending energy, and then start throwing their as much electrons as we have available in this system. Does it make sense? Or at least no one objects. And as a just very quick connection to the class material, let me here. So molecular orbitals are this is overall wave function, multi-electron wave function, and orbitals are those individual objects that depend on positions of atoms. And in big molecule, there are like 20, 100, and so forth of these orbitals. So, what is our practical goal right now? We do need to go over this list. And one more comment. If the occupied orbitals have negative energies, it means the molecule is stable. As it's another signature compared to total energy. So total energy must be negative, and occupied orbitals must be negative. If they, by some reason, become positive, it's a signature that something may be not ideal. Okay, so in the list of alpha occupied eigenvalues, we are going to the end of the list and record this number. So minus 0.5066. In then we are going to unoccupied empty orbitals, and we take first out of them minus 0.01010. So we need these two numbers. And let me do it once again. letter Q. So I am practicing BC, which is like board calculator, and I'm taking this number of the first virtual, first unoccupied, and then I'm subtracting the energy of the last occupied. Control C, Control V. So it will be 0.46. Is it big or small number? What are the units of these calculations?
This is an AU, atomic units.
And what is AU? How much, what is a conversion from AU to kilocalories or to electron volts?
It's 27.21 electron volts.
Yes, yes, correct. And I would look into Wikipedia for the. I see. There are some. At least there are 2 volunteers. Someone has removed the list, but everyone. The table is not optional. It's mandatory towards the grade. So everyone is free to select subjects, but it is not free to choose to present or not to present. So for the units, I can just go into browser and type atomic units conversion. Atomic units of energy. And if one, it's boring. Atomic units energy converter. Maybe this one. So another. Let me increase the font. So another symbol for atomic units are Hartree. And it is kind of natural if we are doing Hartree-Fock. Then units for these calculations are Hartree. So I'm typing in the value that we've got in the. Thank you, Joyanta. Yes. So if you get this 49656. So the answer is 13.5 electron volts, 1,300 kilojoules per mole inverse. So in all units, including the temperature, so it will correspond to 156,000 Kelvin. So is it large or small number? How to interpret this? How to interpret this value? What to compare with? So in order to this band gap energy is important for 2 purposes. One for cover, second for conductivity. So the materials with gap equals 0 are either metals conducting electrons or reactive species ready to participate in vivid reaction. The materials with this band gap of the order of 1 electron volt are semiconductors, and materials with this energy about 4 electron volts are and more are dielectrics, which makes sense. So titanium dioxide, if it is solid, not solvated, it is dielectric. So also let's take this number and I can convert it myself, taking this value that we have computed by subtracting HOMO and LUMO, and then multiply by 2712, so 13.46. Another little calculation: if we want to find the wavelengths in nanometers, we need to 1242 divide by energy in electron volts. Sorry, I have a digit that I do not know. So it is this 13 electron volts is like 92 nanometers, which yes, large use. Thank you. It's like far UV, so it definitely will be not colored to the human eye. And this is like minimal scientific conclusion about this molecule. All of these conclusions are correct if we trust the Hartree-Fock method and Lionel 2DZ basis set. And as sober scientists, we need to have a healthy suspicion to anything we are doing or anyone else is doing. Like, maybe there is an error in this. Maybe there are better method. And indeed, I see the question from Giant. I will repeat. So, indeed, Hartree-Fock is not the most accurate method. It's accurate only in qualitative sense, but for exact numbers, today we have much better methods. We are practicing a lot with Hartree-Fock because there are justifications for all steps. So question from Joyanta: could you please repeat how you have taken two values of energy? So I'm looking on the table. The border of conversion from OCC to VIRT. So in the line for OCC, I take the last value. In the line for VIRT, I take the first value. So this first value of VIRT is called, is called LUMO, lowest unoccupied molecular orbital. And in some sense, I know I shouldn't type it in the calculator, it will tell me that it is an error. So energy of LUMO is this much. Not home, but HOMO. Yes, correct. So energy of HOMO is the last occupied. So it's last orbital occupied. Control C, Control V. That's fine. I do typos all the time. We can look and fix the reasons for different values can be multiple. One of the first thing to check is the coordination of oxygen to titanium. It should be in tetrahedral. Second thing is to check interatomic distances. And if these two tests are going through successfully, then we can look for other reasons. So I will turn into the mode of assisting in the one-to-one fashion. But before we go to this, let me suggest that the homework is written in the lecture notes, but I will resend it once again. So the homework assignment for the Monday is as follows. Please compute the gap between HOMO and LUMO for single titanium hydroxide, for molecule with 2 titanium, 3 titanium, 4 titanium, and report the trend, how the HOMO-LUMO gap depends on the number of titanium atoms. And I'm very interested in exact numbers, and the expected trend is that the larger the number of titanium atoms, the smaller will be HOMO-LUMO gap. Okay, so if any of you are rushing to other activities, there will be nothing new for today. I will be only assisting and helping. So if you need to be elsewhere, feel free to disconnect. I will stay here and go one by one and check if you have if everything goes well. Please type the question. Joyanta, are you asking about homework, or you asking someone else, not me? I will homework. Okay. I plan to send it in the email, but let me type it quickly. Compute ground state electronic structure for a sequence of oligomers with 1, 2, 3, 4 titanium atoms. Hydroxide. For each model, find band gap energy of LUMO minus energy of HOMO. Report the trend. Joyanta, is it sufficient? Or I'll ask a different way. Please type or say if it is insufficient. No answer means you're happy with this explanation. Okay. I am going to so to exit this board calculator, quit, and I'm going to inspect directories one by one and see if oh, you're welcome, and see if you have the right files there, and help if needed. Let me go to Alicia first. Test.com, test.txt. So copy from Dmitry Web 10 titanium oxygen 4H4 into here. So Alicia, I did copy both input and output files into your directory, and you may want, just for your curiosity, to practice this more space in this output file, and see if you identify things we are talking about. And also, you are very welcome to open these files with Gauss view. So you can type gview exe, and then name of the either input or output file. Later on for your project, I think you will be provided with input geometries from assisting grad students that you may use to run the jobs. But if you get a little hands-on experience in looking into this output file, it will make you very confident and ready for next steps. Alicia, does it sound like a good plan? Do you have any questions? You can either, if there are questions, you can either say or type. Okay, it sounds like there are no questions, or they are postponed for later. So now let's go and see. I'm not making preferences. I'm just looking to the files as they appear in the list. So in the file by Kristen. So today is 24th. There is a log file for single titanium, and there are files for 2, 3, and 4. So grep oc log file, grep virch log file, and then I can do vi gap. I'm going to head. Yeah, Alicia. Yes, yes. Thank you for joining, and you spent much more time than needed. I'm impressed by your dedication, and feel free to send email or ask in any way if you have more questions. But I think you did really great. Thank you for attending. Okay, so Kristen. Vi get 1, and I'm going to save, edit, copy. Just trying to organize the data. DD for delete. I insert, enter for next line, escape DD I for insert. So energy homo Some people skip the abbreviation for molecular orbital because of the laziness. Energy of LUMO. And then I'm just contributing to organizing available data for the homework. BC subtracting LUMO minus HOMO and multiplying everything by 27.12. Control C, quit, VI gap 1, electron volts. And okay, and if we want to quickly inspect the for example, file is 2 with 2 titanium in the directory of crystalline. I just quickly check how things are going. So PDB titanium 2. Okay, so Kristen, before running, one needs to fix the geometry. And please, I've just finished the log file for titanium 2. If you didn't do optimization, you probably may want to do it. So and I invite everyone in the audience to contribute and share the experience. So a lot of you are skilled chemists with very strong background in the inorganic chemistry, and you may share with each other insight why coordination of ligands to metal atom is critically important. So right now, in the model that is provided here, this both titanium ions are coordinated to 4 oxygens in a square planar. And titanium, so we are not in the inorganic chemistry class, I'm not going to prove it, but the coordination between titanium and oxygen is much more energetically favorable when it is octahedral. So this can be achieved if the oxygens, 2 oxygens to the left and to the right from titanium, these groups are twisted by 90 degrees. And let me check quickly if the broomstick will work here. No, broomstick didn't work. Okay. So in order to avoid it, I would start in the Avogadro with G chemical, which gives right tetrahedral optimization. But I can try quickly do optimization with molecular mechanics.
Hi, Dimitri, I have a question.
Please.
So because my Gaussian view cannot display the molecule structures. So should I convert the log file to PDB and then open with Avogadro to check if my structure is correct or not? Or is there other ways to do that?
Oh, convert log file into PDB. Yes, yes, it is a good plan. And actually, if you download log file into your local computer, you will be able to probably you will be able to open it in Avogadro right away.
Oh, good, thank you.
Okay, so I'm doing a little silly thing by doing optimization, and it may not. Oh, cancel. Instead of UFF, I wanted to do different force field. View it in goes view. Also, there are several viewers. JMO is installed and should I think it should work on the cluster. Oh, okay. Yeah, I see, Kristen, you did it quicker than I was able to do anything. Let me check. Okay, path node optimized. Yes, excellent. You got the idea. Perfect. So it's good to start and compute energy. And if I think, well, safer to do single point energy for this file. But as an experiment, one can try to do broomstick and check if it will just slightly optimize distances but keep tetrahedral. So I will not save, I will just do as an experiment. Click broomstick. No, no, it's broomstick is not working, so I wouldn't recommend it, and I immediately close the file so it doesn't make situation worse. So just do the one that you got optimization with G chemical. Later on, so Hardy-Fog doesn't give good optimization, but later on when we switch to DFT, one can like do whatever B3lib DFT, Leno 2DZ, optimize, and then it should give reliable geometry. Okay, so let me check. I think Kristen is in a good path. Let me check other directories. ls minus OT. Kristen, Alicia. I will not check what Dmitry is doing. I will go into you. Lab 10. 10. Uh-huh. Super. You're so quick. I'm I'm impressed. The I'm impressed by productivity, but for the results we need to look into them. The values of the trend of total energy getting down is of course correct, but the gap should become smaller as we get from smaller to bigger. So let me open let me open the files and see how they appear visually. File open. View. Again. So the geometry for 3 titanium looks correct. It's qualitatively correct, and it's a good starting point. So the results for 3 titanium are expected to be qualitatively reliable. Let me look for other geometries. Open 2. And for the 2, it also looks correct. I don't know if you started from this geometry and got small gap, it's a little strange. I would be interested to explore why. Let me check for the log file. And
It's in the director, not in the lab.
not in lab 10. I'm looking.
Some other one titanium.
Let me focus on the log files. Log files. Go one order up. Optimization. Okay. Gaussian job may still be running or didn't terminate normally. Okay. This geometry is not ideal, and it may bring errors in the electronic structure because of the angle between titanium, oxygen, and hydrogen is 190 degrees, and it should be like same as in water. So because the oxygen has lone electron pair, and so let me maybe click broomstick quickly. For single titanium, broomstick should give good results, or at least good starting point. So broomstick. Okay, so now angles for hydrogens are like 100 or 108 degrees, and I will save it. File, save. I will add broomstick, broom.com, and rerun single point. Calculate. Gaussian calculation setup. So job type, node optimization. The Harty-Fock is.
I think I have another file named with energy. So you open the optimization.
But yes. But here I already modified geometry by the broomstick, so I'm continuing from there, selecting energy, Harty-Fock, and submitting. Save. So it has this ending broom, because yes, override, and it should ask if we want to submit it to Gaussian. Okay, and it should be done by now. So I'm going back to the command line, and -nt, and exploring this log file from the broom. Ctrl-C, So we have HOMO minus 0.5 atomic units and LUMO minus 0.01.
Oh,
So you see a little angle between hydrogen and oxygen changes energy drastically. So there is a correlation between geometry and electronic properties. Okay, I think you are on. Yeah. Oh yes, I'm listening.
But because my Gaussian view cannot display the structures,
I
how can I?
I understand. I understand. This is a little challenge, but we will depart from Gaussian from Gauss view very soon.
Question.
Yes.
So for my titanium 2, I click the broom before I do the energy calculation, but the results still not good, right? I click the broom before I do the calculation.
No. For do not click the broom. The broom just by good luck works for single titanium, but broom generally is not reliable.
Okay.
So if since the molecule is quite small, try to do DFT with the same basis set, like DFT bis relief with Lanu 2DZ, and then optimize if you really want to explore this, and then it will be good. So I think you are on a good track. Let me check. I see question in the chat room. So Jayanta asking, in the case of titanium hydroxide, we are using Gauss view, but oligomer case, we are using Avogadro. So Jayanta, the way how you create geometry is more a question of personal taste. So if you can create good model with Gauss view, it's perfect. If Gauss view is not working or you do not feel comfortable, use another software. And Gauss view and Avogadro are not the only pieces. So one can try JMO or HyperChem, or there is well, ChemDraw 3D. ChemDraw 3D can also create molecules. So it's just matter of personal taste. Okay, let me go further. Kristen, you, Alicia, Dmitry, Janis. Okay, let's go to Janis. Uppercase Janis. Less minus OT. Lecture 9, I think. Okay, let's look into lecture 9. Grep OCC, titanium 3, log.
Something went wrong with the titanium 3, so I'm gonna have to go to Avogadro for it. Titanium 2 looked okay. It looked decent, but it wasn't great either. I don't know why, but it doesn't seem to be optimizing much. So but I'll just go to Avogadro here real quick and do a chemical calculations rather than LAN L2 or instead of LAN calculations.
Oh, Kristen is typing that she's disconnecting. Kristen, yes, thank you for joining. You are welcome to disconnect. And I think after Janis, I need to look onto Mahima, and then we will be done for today. Janis, I do see that HOMO is minus 0.5 and LUMO is minus 0.11. So the gap will be like 0.4 atomic units, which is like 10 electron volts. So it's smaller than for monomer, and it makes sense. I didn't watch the geometry, but based on HOMO-LUMO gap, it doesn't look too suspicious.
The main problem, though, is that the titanium atoms are, during the calculation, they're somehow getting bonded together. So if you look at the geometry, it's very screwed up. It doesn't look right at all.
I will look in it, but never trust these lines that connect atoms. It is just an artistic way of drawing the molecule. So it is not. If you use if you check different piece of software for.
Not just the bonds either. I think the actual structure looks wrong.
Okay. Yes. Were you optimizing with Hartree-Fock or force field?
I was. Yep. Not universal force field. I was using LAN L2 DZ.
LAN L2 DZ is the basis set.
Yep.
And
I was using Hartree-Fock though.
Okay, Hartree-Fock doesn't have a good reputation to give reasonable geometries.
Yeah.
So it's better to. So connection between titanium is nothing. I wouldn't worry about it, but I would move. Yeah, maybe starting from redo it in Avogadro once again would make sense. Or another option is same as I suggested to you, is use. It will be way ahead of our theory class material, but use DFT. So instead of Hartree-Fock, select
DFT.
Yes, DFT. Keep line to DZ. Do instead of energy, let's do optimization. And maybe it will be just quicker than transferring files. You must save Gaussian input. So.
Okay, I'll give that a shot.
I'm already doing it, so we're just cooperating on this. So optimize DFT B3 loop to DZ. Save. And it should ask if we want to submit it to Gaussian. Okay. And optimization with DFT will be not in like 2 seconds as a single point. It may, if it is straightforward optimization, it will be like a minute. If it browses through local minima, it may take, even for the small molecule, like 10-15 minutes. But I see that you are on a good track. Yeah. So when the job will be done in reasonable time, and you will see it in your directory, and also.
Yep, it looks like it is in the directory. Yeah.
Also, let me show something. See, watch, tail, file, apostrophe. So this watch command allows to monitor as file is getting incremented in real time. So one can see if it how it develops. So when if you look on other files, like if you do not do it in Gauss view, tail titanium 3.h.log. So at the end it shows normal termination, and if you look on the on this long file, it seems not having this normal termination because it's still calculating.
Okay.
Okay. Mahima did leave, but I'll check her directory once again. Yeah, Janice, I think you are on a good track. I just, before we all disconnect, want to check what is going on in. Oh, nothing is going on. Let me copy. Copy web 10 titanium or. Everything to her directory. Okay, at least then. No, this way. Okay. So I'm open to any questions. I think we did I check into directory of Jayanta? I do not remember. Huh, Jayanta, you do not have anything in your directory. Not good. Please, and it's not good. It's not good. I'm sharing files that I did in my directory into your directory, but you need to pick up. It will be too late very soon. So please, if the the best thing is to invest time during the lab when I can help on the fly. If you do it on the like in your personal time, it may take much longer, even for this simple thing. So let's do it with when someone can help. So can you open the files in your directory? Make sure that you can look. Well, type more and the name of the file. Can you are you logged into the photon? You need to not good. You need to open MobaXterm and from there log into the photon cluster. Are you working on your personal computer or public computer? What do you mean one public? Just look online for MobaXterm and download it. And then from MobaXterm, you will be able to log in. And if you are using public computer again and again, you need to download this MobaXterm during each session, but it's very quick. Also, please check the so it's a message for Joanta. Please check QBB 132. I believe this room is reserved for our class. It is equipped with a camera and microphone and computers. So I will stay on. If you are in QBB building, I can wait. You can walk there Monday, okay, but we need to interact. I am now in the lab. Okay. Okay. Type of mistake. That's fine. That's fine. More questions from Janice.
none as of right now. Currently, I'm just moving each of the projects to each different folder. So I've made 4 different directories.
Super.
For each, oligomer and the main monomer.
Very good. Very good.
Yeah.
Well, we both, probably your schedule is busy, my schedule is busy, but once we will find time to exchange emails about continued discussion about research projects, and I have one very wild for brave imagination, the project about the measure of purity for quantum state from single photon emitter. So this is typically, originally this idea was developed for astronomy to observe signals from very weak signals from far stars, and now it is used for also used for quantum information. The project.
I see.
The project that you, Dr. Renk, is working on from experimental point of view, but it is it's very challenging. It will be more complicated than typical project, but if you're interested, I can send more information so that it will be on in your selection list.
Yeah, if you could, yeah, I think that would be a very interesting project to look at.
Okay.
Hi.
Yes.
So I try to use the DFT to calculate the titanium-2. The results quite different from others. So you can open the PI10 and see the number.
Okay.
Value.
Okay. I will go into your directory. So even before I start, I want to make a disclaimer. For comparison of results in a series, one needs to do everything with one method. So if you did optimization with DFT, and then you want to compare results with Hartree-Fock, you need to take geometry from this DFT optimization and do single point with Hartree-Fock. If you would look for HOMO-LUMO gap from DFT calculation, even if the geometry is perfect, it will be much shorter. And if you need to a comparison with experiment, DFT gap will be much realistic. We just in the class we are not ready to absorb theoretical ideas behind DFT. The calculations are quite simple, but we need to understand what is going on. We need to go through few more concepts. Okay, lab 10. Normal termination. So the gap here, no, even for DFTs it seems too small. Is like it's like 2.5, 2.4 electron volts.
It's very small.
It should be bigger. Let me open it. It's interesting. Open. One more step. View. Log files. Lab 10. DFT. This loop. It looks like you were doing single point rather than optimization, by the way. I don't remember if you were doing it or I was doing it, but whoever of us was submitting the job, I have a suspicion that it was energy rather than optimization. And for DFT, we need to select, let's select optimization.
For DFT, we have to select optimization.
Yes, yes, to change geometry. Okay, and let's check for method. Run it to DZ. This relief, okay. Submit, and I will update the file name. Would you like to save input file name? No. So I will add the word, instead of energy, I will type optimization. Optimize. Save. Submit to Gaussian. Okay, and I do not look forward to get instantaneous answer, because it will take some time. So yes, I'm listening.
So because all the previous calculation HF, we use the energy, not the optimization, right?
So energy means take the geometry that you have,
okay.
like nail down all ions where they are, and solve time independent Schrödinger equation for electrons only. And optimization means find, solve electronic problem, compute forces, and move atoms a little bit. Then do it once again, find forces. So it's two types of problems cycled together when you do optimization. And it takes longer. You see, your optimization of titanium 2 with vinyl 2DZ is going on, and the optimization titanium 3 for Genesis is also going on. So it's a little more expensive calculation, and Photon is just a it's slightly bigger than the regular desktop. It's just a server to process, to store files. It's not a supercomputer. As soon as we get to bigger jobs, we'll start uploading and running them on actual supercomputer, when everything will be like instantaneous. So Janice, you may also, if you have like free time, steam, and energy, you may try to upload these input files into CCast, submit, run job there, and you'll see that it will be a fraction of a second for the same job that we are waiting for like half an hour here.
Okay, I can give it a shot a little bit later. Right now I have to get some other things done.
Sure.
So for now I'm going to disconnect.
Okay.
And I will continue this tonight. I will double check on it as soon as I'm done with some of the other things I got to do here. So.
Okay. Okay. Very good.
All right.
Yep.
Thank you so much.
Oh, thank you. Thank you.
All right. See you later.
Yep. See you.
Bye.
I'm just curious, why the titanium 3 works for HF carbon block, right? Kind of works, but titanium 2 is problem.
The okay. If the geometry is selected correctly, then there will be no problem for Hartree-Fock to compute any number with reasonable qualitative results. The problem is find optimal geometry, because neither force field nor Hartree-Fock are designed to optimize geometry with transition metals. If you would take some simple hydrocarbons, everything will be simpler. But I intentionally want the course to include this a little bit challenging metal-organic complexes, because a lot of researchers need to compute system with transition metals, and transition metals need special treatment. So basic methods fail for geometry optimization of systems with transition metals. So it's not only interatomic distance but also steric angles, and it's objective challenge. But DFT is expected to give reliable results.
So it takes super long to do the optimization with DFT.
No, it's not super long. The Photon is not very powerful computer, so it's if you would submit the same job to a supercomputer, it will be like 1 second. So and we shouldn't sit and wait until the job is done. The typical attitude is if you do computations, you submit like as many jobs as you have mood for, like 20 or 100, and then you go and do some other activity and return back to them in a week or in a day and check if they are completed. So it's a standard and normal attitude. So if they, it's not practical to like sit and wait single job to complete while one can prepare, like human and computer should optimize their interaction. Sorry, I didn't answer on a couple of your emails, but I see Svetlana did answer. Oh, are we done for the course activity for today?
Yes, but the Avogadro cannot open the log file.
Okay, then thank you for letting me know. Then we need to convert log file into PDB.
Okay, great, thank you.
Okay, so if we are done with class activity, I will stop recording, but if we need to talk more, I can stay online.
Yeah, I'm done. Thank you so much.